In the second part of this tutorial, we are trying to understand how the data is cooked, how we go from CSV files to something readable about our model. And so it's already implemented here in SRC data. And let's try to understand the code here. And so by the end of this tutorial, you'll be able to customize these to your particular task. Well, we've got some code here, it's nice, but let's also have some Jupyter notebook running where we can play around with this code and basically understand what's happening here. So that's why I prepared some template, and in this part, in the second part of this tutorial, we're going to cover two subparts of this notebook. So reading data and performing some basic exploratory data analysis, and then we'll create some PyTorch datasets and data loaders. So these two we cover in this part of the tutorial. Right, so first of all, we start with some CSV files and we use pandas to read data. I'll spend just 2 minutes explaining the task itself. So you'll have your own task, and I really don't focus here on the task itself, so we discuss the training pipeline. But one of my current projects is classifying research articles into sustainable development goals. So these are 17 goals for humanity, which cover tackling poverty and hunger, and then providing clean water and clean energy. So it's really a nice task to trying to understand how research contributes to achieving these humanity goals. It's a very interesting project, and I hope to shoot a video, give a talk on this project. It actually shows how NLP, even simple text classification cannot be simple if you don't have really easily accessible training data. Right, so let's read some data. So these are the 3 files that I also provided in the config file. So we'll have a training file, the validation part, where we check our scores, and then probably our test file that we would like to run prediction against. So these are actually these 3 paths are provided here in config file, right? So this you can customize. So you provide path to your data, and then training file name, validation file name, and then test file name. Right, so what do we have here? So we have an ID of an article. So here it's called EID. Then we have the target, so just an integer. And then these are research papers, and we have a title, we've got keywords, we've got an abstract. And to combine this somehow, we just concatenate titles, keywords, and abstracts, and this would be our input text field. So if we took a look at this this field called title underscore keywords underscore abstract, so these are all concatenated, and I only introduced some delimiters, so title, keywords, and abstract. So it's just trying to distinguish these 3, but I already provided them in you see in these square brackets. So we can actually make BERT model use this information that that the text field starts with the title, then goes keywords, then we have abstract. So for now it just serves as some delimiter. We can basically ignore that, but a bit more advanced level of using BERT would be providing these special tokens in square brackets, so providing these to BERT vocabulary. Okay, right, so this is a toy file, and so we see that we have only 5 classes here. So 1, 7, 8, 12, 13. We can go back and see that it's about poverty, then number 7, affordable and clean energy. So number 8 is decent work and economic growth. 12 is responsible consumption and production, and 13 is climate action. So it's actually a subset of these 17 goals. So we have only 5 classes here. And yeah, it's good to check class distribution in all of the files. Well, maybe in test dataset, maybe we don't have any labeled data, but now we see here that we have 4 classes in test data. Well, but that's not much important. You'll have your own class distribution. And before using BERT models, it's a very nice idea to check the length distribution. So you take your input text field, and then yeah, this simple piece of code just shows the distribution of this input text field in words. So we just split by white spaces. It's important because it's BERT and basically transformers have their limitation that they don't work well with long texts. So basic BERT implementation can handle up to 512 tokens. Well, with GPT it's 1024. So that's why it's really important to analyze the distribution. So in our case, we see that our median text length is about 200 tokens and maximum is 564. So if we cut at 512 tokens, so it's not we don't lose much, right? So, well, maybe we have some large pieces of text which will be truncated, but basically we fit pretty well into this limitation of 512 tokens. So supporting long texts is currently only being researched. We have these reformers, long formers, these big BERT models. But yeah, it's being researched and the most popular BERT implementation handles for now up to 512 tokens. So it's good if you remember before just throwing, all the Wikipedia articles, so some really long texts, before throwing these into transformers, it's important that you analyze your input length distribution. Okay, that's all about pandas and initial exploration. Let's proceed with preparing data for training. So it's about PyTorch datasets and data loaders. Right, so here I just copied the implementation of the PyTorch dataset. So I just copied it from our repository, and let's just try to understand what it's doing. Right, the whole idea of the dataset, so first of all, is basically having this method getItem, which given an index, it would produce an element of the dataset. So the notebook will be pretty dirty. The whole idea will be to understand all the parts. So I'll be writing some temporary code, but the idea is that we really understand this, and you'll find a cleaner version of this notebook in our repository as well. Right. So basically, the getItem method is let's provide a small example. When you initialize a simple Python list, and then you do something like a, and in square brackets you provide some index, then basically it's using this getItem, so this underscore getItem underscore, it actually is responsible for this operation, so taking an element, given an index. And so we would like to do the same for a dataset, and that's why the main part of this class is implementing this getItem method. But let's look at what it's doing. So in constructor we pass our texts, which is a list, and I really recommend, it's a good practice to specify types. Well, here goes all this holy war about typings in Python, but now the community drifts to actually using types in Python. Well, so we provide a list of texts. So this will be our input text, titles, keywords, abstracts, concatenated. Then we also provide labels, also as a list of strings, and it's optional, so it's initialized with none, meaning that we can have a test dataset without labels. Then we'll need a label dictionary, mapping these labels, so which can be strings, mapping these to integers, And well, for training dataset, it will be created on its own, but probably we'd like to provide it to a validation set. And then, yeah, even though we discuss model further in the third part of the tutorial, but we here in the dataset, we'd like to process data, we'd like to do tokenization, and we would like to know which tokenizer to pick up, and here we therefore provide the model name. And we'll be using basic, well, a very simple DistilBERT based uncased model from HuggingFace. So here for this dataset, we basically need these two arguments for tokenizer. Right, and so then in constructor we'll just save all these attributes, and then we create a label dictionary. So yeah, basically it will map class 1, a string that we provide, to 0, then class 2 to number 1. So here it can be really descriptive label like poverty, you know, clean energy, and anything like that. So we just store this dictionary. And then we initialize a tokenizer. And yeah, these parts, these would be just special tokens. Okay, actually, I'm not sure that we need it, so probably some legacy. So let's, yeah, stop here, that we initialize a tokenizer. Okay, then we have two more methods. So len is a very simple method, which in this case it just returns the length of the list of texts that we pass. So basically we would like to know the length of this data set. To jump a bit ahead, we'll create a data loader instance in PyTorch, and data loader would like to know something about the dataset, and basically it just needs to know the length of the datasets, and it needs to be able to take an item from a dataset given an index. So that's why we need these two methods. Right, we see length is a very simple method. Well, I don't handle exceptions here. Yeah, what if we provide an empty, well, if a list is empty, it's fine, so length will be just 0. But you know, if we just provide not a list, but something, yeah, something inappropriate here, I don't handle exceptions, but at least we can have typings. Yeah, at least we know that text is a list of strings, basically this is a simple implementation, and we don't handle all exceptions here, but we keep it simple, right? So it's just length of the input list of texts. Right, okay, so let's then dig into the most interesting part of this dataset. Here is this getItem method. So we would like to process the input piece of text, so create some representation, and let's understand what we need, how we pass our text into a data load and then further into the model. Okay, so first of all, given this index, we take a piece of text. And then the most important part happens here, and it reuses HuggingFace tokenizer and then the method encode plus. So let's understand what's happening here. Okay, I'll just copy this piece below in a cell, and then we'll customize it and play around with it, trying to understand what's going on here. But first of all, we'll need a tokenizer. Okay, right, so let's initialize HuggingFace tokenizer. So you see, it needs a model name. So it reuses as simple utility auto tokenizer from pre-trained, and then you can just pass a model name and it will pick up a appropriate tokenizer. So yeah, that's very handy. So we can just initialize model name. So we'll be working here with DistilBERT base uncased. DistilBERT, yeah, you can read about it. It's a lighter version of BERT. So it works almost the same in terms of accuracy, but it's distilled, so meaning that it's lighter, and then it runs much faster. So it's a base version, meaning that it's not large, and uncased means that we ignore cases here. So we work with lower cased text. Okay, so we can actually initialize it in capitalized, so it is a hyperparameter. And so then we provide this model name to this method from pre-trained, and then we take an appropriate tokenizer. And here it's good if you are connected to internet, because it basically then we further load weights with via the internet. So okay, this tokenizer then is we can print it, and it shows that it's pre-trained tokenizer. It knows its name, and we can see some more parameters here. Right. Okay. So then we use this tokenizer to encode our piece of text. So let's just create some piece of text. Well, X is not the best descriptive name. Let's just call a variable, create a variable input text, and then anything like I enjoy playing football under rain. Okay, and then we'd like to encode this piece of text, and what it's doing, it adds some special tokens with this flag, and then we'll be actually truncating or padding this to max length. So this parameter max length, for this toy example, let's just specify 16 here. So this padding means that we will take this short piece of text, and then we'll enlarge it with some special symbols up to length 16. That's pretty important because, the model will be able to work with inputs of the same length. So that's why we specify here, first of all, padding. So short pieces of text will be straightened to this length. And then truncation means that long piece of text will be cut to the first 16 words, or to be more precise, word piece tokens. So we'll take a look at these word piece tokens. Right. Okay. So let's finally see how it looks like, and then there will be more commands. Okay. So it creates some dictionary, and we see that here the input is encoded. So we have a key input IDs, which is basically, you see, a list of integers. So yeah, we see input words, and then they are somehow encoded with some numbers. So we'll try to understand that. And then attention mask is just, a list, or in this case, a tensor. So we put a flag return tensors, meaning that PyTorch tensors are returned. And then we have attention mask, which basically just distinguishes our words from padding. So we'll see that we are padding our piece of text with special symbols up to length 16. And so here in attention mask we'll have ones where we actually have real words versus zeros where we have padding. And it will be very important for the model to have this attention mask to know, the model will know where we have some real information. So in the BERT model or in transformers under the hood, there will be all the special mechanism attention masks, and it's important that these attention heads, so that that this mechanism don't work with padding, so that they only take into account some real information that we provided, so our piece of text. Right, okay, so let's understand how this processing works. So we have some IDs here, so what actually stands here, what they mean. Right, so we have our tokenizer, and it has a method get vocabulary, and we've got a vocabulary. Okay, we can see that it indexes some words, but they look a bit strange, right? So number 0 is a padding token, so that will be exactly this special token that we add to the right to our short piece of text to up to length max length. Okay, this is a special token, and we see it's in square brackets. So square brackets mean special tokens. And then we see there are a lot of unused tokens. So they go yeah, up to 100 here, but then further from 104 to 999 actually. So almost 1,000 unused tokens. So that's for a more advanced usage. You can customize your vocabulary. So you can provide some special tokens in square brackets and add them to vocabulary. And here you can add, you know, mathematical formula, anything, any unseen tokens. And so basically what I showed previously, we can extend, we can add titles, keywords, and abstracts as special tokens to the vocabulary. And then starting from token 999, here goes exclamation mark, and then all the other words and actually parts of word. So let's save this into some intermediate variable, VOC, and let's take a look at the length. Okay, it's something about 30,000 words, and we'll see that word parts here. That looks like a lot, but actually it's not, right? So it's 30,000 as compared to some RNNs and LSTMs. Well, it mostly depends on the text processing that you use, so not on the model. But if you work with words, and if you'd like to store all the words in your language, that might be much more than 30,000, right? So one of the drawbacks of some simple models like char, RNNs, or LSTMs with simple processing where you store all the words. So one of the drawbacks is that you have to store embeddings for all of your words. So you might have a vocabulary of length 1 million, and then you store a million embeddings, so vectors of size, let's say 300. And this embedding matrix itself is already something about 300 megabytes in weight. So it can actually occupy some 90% of all the weights in your model, only this lookup embedding table. So here it's done much more efficiently with word piece. So I'll just leave a comment here that BERT works with word piece tokens. So you can read about it. We don't cover it here, but it actually works on subwords level. Instead of words, we have subwords. And that makes it much more efficient, and we can handle, we can work with a vocabulary only about 30,000 words and subwords. Right, and so let's see how this, what's actually being done for the input. So we, for that, let's create an inversed vocabulary. So going from IDs to tokens instead of this original vocabulary. And then we'll be able to understand what's happening here. So let's create an inversed vocabulary. So we need to go through all the items in the vocabulary and, well, inverse them. So we'll go through all the keys and values in vocabulary items. And for this, we need to create a mapping from values to keys. Okay, and then inversed vocabulary will look like this. So we map an ID to some token. And now let's take a look at this tensor, and let's see what these IDs actually stand for. So we need our output dictionary and the key input IDs. Let's convert them to list. It's easier to work with lists. Okay, it's nested, so we'll take index 0 here. Okay, and let's see what these IDs stand for. So we will create this simple list generator, inversed vocabulary I for I in this list. Okay, and this is what's actually happening, how we'll represent our input. Yeah, we can actually create a string, so joining this with spaces. Okay, so we see that we first add some special token called CLS. Then we'll have our input words. Then we'll finish with a separator token, and then we'll pad it all to max length 16. Yeah, here when we discussed vocabulary, I skipped unintendedly, I skipped these IDs, but they are very important. So here are around 100. Yeah, we have unknown tokens with ID 100. So everything that cannot be represented with this vocabulary gets an yeah UNK in square brackets. And then we start with CLS token and then end with a separator token. And it's called a separator because transformer can handle pairs of sequences. So we can have input 1 and then separator token and then input 2 for some tasks like sentence pair classification or question answering. And then we'll have a special mask token. It's more about the task that BERT was pre-trained with. So masked language token, masked language modeling, where we replace some tokens with a special mask token, and then the task is to recreate them. So you throw off some word from input, replace it with a mask token, and then you have to predict this word that we threw off. Right. Okay, so probably shed some light what's happening here. So when we use the encoding to just process our input text, and then we add all these special flags, yeah, to truncate, to pad it to max sequence length, and then to return also the attention mask. Right. So, and now we can see that attention mask basically just yeah, it's just zeros and ones. Okay, we can do the same, convert it to list. Okay, right, so then it basically just says that we need to look at the first part, and then all these padding tokens will be basically ignored. This information will be available for the model, so this will be passed to the model. Okay, right, so that's about the training set. That's about the text classification dataset, and let's just initialize the dataset and see what it's doing. At this point, let's go back to our code and let's try to understand some further parts of this code. Okay, that was all about initializing this text dataset. And then what we'll be doing actually in this method read data, it's just reading data from CSV files, and further we create training dataset, a validation dataset, and a test dataset. Okay, so let's take a look how this dataset, how it looks. Right. Okay, of course, if we defined some class, it's interesting to see how the object would, how the instance of this class would look like. Okay, so we need to pass texts, and let's change here a bit. Yeah, we don't have params here, so we'll be passing from our training data frame. We'll text the field. We'll take the field title keywords abstract, and we just pass these as a list. And then labels, it can be a list or actually an NumPy dictionary would work as well. So here we take our target ID, which is called SDG ID. Okay, it was defined as a list, so let's provide a list here. For the purpose of a small example, let's just take 16 as a max length, and here goes again model name, which we initialized as distilled BERT based on cased. Okay, so the training dataset is defined, and we can see that now it has a length 150. Well, we can call len for this training dataset precisely because we identified this this method len, and now we can take items by index. So if we just provide some index here, yeah, it returns a dictionary with attention mask, with features. Let's see what features stand for, and then targets. And now let's go back to the definition of our getItem method. So we understood this part, about tokenization and encoding. And then some final things that we did here is, well, here goes Catalyst. So its requirement would be to have a field called features. Well, this is customizable. We can change this actually, but by default, Catalyst would like to see a field called features, and it's exactly the same input IDs. We just basically rename it with features. So squeeze 0 here means that we, basically, tensors would like to support several objects, and here for only one object, we would like, instead of these nested lists, instead of this nested tensor, we see a tensor and then a tensor inside. So we'll just take this inner tensor. So that's why we need squeeze 0 here. Okay, so we'll have a field called features instead of input IDs, and then encoding targets. We'll just take. Remember, we passed an index to this method, and then we take an appropriate target, and then we actually just look up in a dictionary. So we take a labeled dictionary, we get this item, also then some squeezing, and return it as a tensor. Okay, let's look into that. Right, so this dataset has also learned a labeled dictionary. So it's an attribute called label_dict, and we see it's here it simply maps IDs that we provided to some integers. Well, starting from 0, we passed label number 1. It maps to 0, 7 maps to 1, 8 maps to 2, 12 to 3, 13 to 4. But if we were to provide labels as strings, this would be mapped. So then here we'll have strings mapped to these integers. Okay, and so for this example, we had a target, just a tensor with only 1. It means that it's it was class 7 actually. Let's look it up in our original data frame with the same ID 17. Let's maybe take values here. Okay, indeed we had class number 7 here, and so further we had some titles, some keywords, and some abstract, and the same combined. Well, indeed, it was some ID, and then SDG, so our target class number 7, affordable and clean energy, and here it mapped to index number 1, and so that's why here in targets we have number 1. Okay, so here we understand how training dataset looks like, and let's then go further to this data.py. So once we've created training dataset, a validation dataset, and a test dataset, further we create data loaders. Data loader is a pretty simple utility that takes a dataset and then it creates batches, so it splits these into batches, and it can also shuffle data. And let's look how, what it actually is doing. Again, for Catalyst, we'll create a dictionary with keys train and valid for training and validation data loaders, and then a separate one for a test data loader. Okay, let's see how this looks like. Right, so for this purpose we will create a validation dataset as well. So basically it will look the same, only that we'll pass a validation data frame here. Okay, and we create a dictionary with 2 data loaders. Let's fix some batch size. We'll discuss it when we switch to training. So batch size is a very important, well, not the most important hyperparameter in your training, but we'll work with GPUs, and batch size actually really affects whether you would fit your data to the GPU. So you need to actually tune batch size carefully to use with GPUs. Right, so actually, yeah, if I run if I'm running here, it's on CPUs, it's better to have some small batch size, let's say just 2. And then a data loader can shuffle your data, and it's a good practice that you shuffle your training data set to avoid such scenarios where you have all labels of one class in the beginning, but all labels of the different class in the end. And it really helps if you shuffle your training data. But as for validation and test data, typically you don't shuffle them. Okay, so we created this dictionary with 2 data loaders. So this will pass to Catalyst. And let's look how a data loader works. Okay, let's take train here. Okay, we see it shows it's a Torch utils data loader. So basically what it's doing, it's some sort of an iterator or generator. Well, if we try to take a next item, it says the data loader is not an iterator. Well, to be honest, I don't remember all the differences between iterator and generator. But basically, to look at the first element, you can convert it to iterator. And it's not the most memory efficient thing to do this, but just to look into the first element, we can do this. Convert this to iterate and then taking the next element. And here it's basically the same what we've seen so far, only that now it's done for a mini batch. So now we see that it's, let's call this a mini batch. And then we see that a mini batch is again, it's again a dictionary, and we can take features. And now it will be a tensor with sizes 2 by our max length by 16, right? So if we take a look, now it's a PyTorch tensor, right? So we can take a size. And now the 0th dimension is a batch size. So it's 2 in our case. And dimension number 1 is max sequence length is 16. So in more realistic scenario, this will be some batch size, something like 32 or 64, whatever fits in your GPU memory. And this will be probably 512, so your sequence length. Right, so that's all about data processing. So we come from, so we've done all the way from CSV files here to basically creating PyTorch data sets and data loaders. And now we actually prepared our data. So now PyTorch will know how to pass these mini batches to the model to start actually training something. And then in the next part of this tutorial, we are covering the model.